Hello and welcome to the MOOC on optical communications. In this module, which is actually a continuation of the previous module, we will complete the discussion and derivation of the bit error rate or the probability of the bit error for the on-off keying systems, and then compare different receiver techniques as to which one would be better in terms of the sensitivity of these receivers. Okay. So, if you remember what we were looking at in the previous module, we had arrived at an expression for probability that the receiver would declare a bit as 1 when the bit that has been transmitted is actually 0. So, this of course is an error, right. So, when the bit is declared as 1 when the input that has been or when the bit that has been transmitted is 0 would lead to an error. There would also be an error of the same form when the received bit as bit 0 while the bit that was transmitted is 1. While arriving at an expression for the probability of mistaking a 0 with a 1, which is given by this probability of 1, given that 0 was transmitted, we found that this actually is given by this integral of this particular function. Okay. Because this integral is very popular, it comes up in many places, there is a specific shorthand notation that we actually use, and this notation is what we call as the Q function. The Q function is defined by this expression, which is given by 1 by square root of 2 pi and area of the curve from x to infinity. Which curve is that? That is this particular curve. Of course, you can actually push this 1 by square root 2 pi into it. So, you will actually be looking at the area of this particular curve, which I just wrote down in the bracket, okay, and this area from x to infinity. What kind of a curve is this? If you look at this curve, you will realize, if you compare this one with the Gaussian random variable, you will realize that this curve is actually an expression for a probability density function of a Gaussian random variable, okay, that is a random variable which has a Gaussian distribution or Gaussian density function with 0 mean and variance equal to 1. This is called as unit variance. So, it has 1 unit of variance and it is 0 mean, which means that if you were to sketch this function as a function of t, so if you sketch this function that is in this bracket as a function of time, you would see that it is actually centered at 0, at which point it will actually be 1, and thereafter it would go decaying as you go for both in terms of higher values of t in positive side as well as in the negative side. The variance is actually the difference between the points where the function value drops to 1 by e of this one, or e to the power minus 1 by 2 of something like that. Okay. So, it does not really matter. At t equal to 0, this actually has an amplitude of 1 by square root 2 pi, which I forgot. Okay. So, if it drops to 1 by e of this value or 1 by 2 e of this value, that is essentially the variance of this one. But it is important to note that this curve, right, never touches this t axis, the horizontal axis, because the curve goes to 0 only at t is equal to plus infinity as well as t is equal to minus infinity. This curve is also symmetric. Now, on this curve, let us pick a certain point. Okay. Let us call this point as x. Okay. For example, x could be 2.3, x could be minus 1.5, it could be anything. If you look for the area under this portion of the curve, right, to the right side of the x that you have picked, that would actually tell you the Q function. So, in fact, the Q function is defined by lighting these lines, okay, and then evaluating the area. For example, you might try a different x prime value and then find the area under this curve. You are feeling adventurous, you can try this value of x, okay. This time x would be negative, but this would be the area under the curve that you are looking at. So, by writing different lines and then looking at the area under the curve beyond to that particular line, this vertical line that we are drawing, from that point all the way up to infinity, that would be the definition of Q of x function. Okay. If you make x is equal to minus infinity, which is go all the way up to minus infinity here and then look at the area under this particular curve and all the way up to t is equal to infinity, that value will be equal to 1, right, because the area under the probability density curve must integrate itself to 1. Okay. So, this Q of x is basically the area under the curve from x to infinity. So, it is partial area, and in terms of the probability, what it simply means is that the probability that the random variable that you have considered, so call this random variable as x, it will take on a value that is greater than or equal to x is given by this q function, okay, of a 0 mean unit variance random variable, okay. So this is 1 by root 2 pi e to the power minus t square by 2 dt. Now what is the relationship of this q function to our probability of the error? Well, look at this expression here. You have an integral which goes from I th, which is a threshold current, to infinity, and there is a equation or there is a function which is very similar to a Gaussian function, except that the variance of this one is given by sigma 0, the mean is still 0. So the variance is sigma 0 or the variance is sigma 0 square, while the mean is still equal to 0. So if I can rearrange this equation such that it looks in the form of a q function, and q function is well tabulated in the literature. So if I can rearrange this function to look like q of something, okay, then I can use those values which people have already computed many years ago. To do that, I need to just change the variables of the integral, okay. So if I change the variables out here and normalize this one, then we will be able to put this expression p of 1 given 0 in terms of the q function. So let us do that. I will do this as an exercise for n0 and I will leave this as an exercise for n1 when we get to the discussion on n1, okay. So the probability of the receiver declaring 1 given that 0 was transmitted is given by the area under this probability density function, where you are going from the threshold current to infinity, e to the power minus, we had considered n0 here, so let us consider that n0. So n0 square divided by 2 sigma 0 square dn0. So clearly if you look at these two expressions, in place of t I have put n0, right. So let me define n0 by sigma 0 as a new variable t, then I know that dn0 will be given by sigma 0 into dt, and when n0 is equal to I threshold, t will be equal to the lower limit, t will be equal to ith by sigma 0, and when n0 is equal to infinity, t will be equal to infinity. Therefore the integral limits will change, okay. So the integral limits will change, and then we can write down over here the expression. So this expression will now become 1 by sigma 0 into square root of 2 pi. I simply pulled this sigma 0 square from this under root to outside, okay, and the integration limits will change. I th will now become I th divided by sigma 0, infinity remains the same, you scale up infinity by a factor of sigma 0, nothing really happens, and in place of n0 I have to write n0 square is t square sigma 0 square, and n0 square by sigma 0 square is given by this fellow. So divide both sides by sigma 0, so this n0 square by t0 square is nothing but t square. So this becomes e power minus t square by 2, and then dn0 is nothing but dt sigma 0. But this sigma 0 being a constant cancels out after coming out of the integral, cancels out with the sigma 0 that is there in the denominator, and what you get now is 1 by root 2 pi. The lower limit of the integral is ith by sigma 0 going all the way to infinity, and then you have e power minus t square by 2 dt. Now do you see the equivalence with respect to the q function? Yes, you do. This is nothing but q function of ith by sigma 0, okay. So if I know what is the threshold current, right, then this threshold current divided by sigma 0 will be the expression for probability that you get 1 when you have actually transmitted a 0. So the receiver mistakenly identifying a 0 as a 1 is given by this expression. Now let us proceed to find out an expression for the similar probability of error, which is probability that the receiver will think you have received a 0 while the bit that was transmitted was 1, okay. So this error, if I want to find out, I have to look at the sample current at the sampling time ik, but this time I know that the bit that I have transmitted is actually 1, right. And what would be the photocurrent when you have transmitted bit 1? Well, the photocurrent will involve whatever the transmitted component, the photocurrent corresponding to that, plus the noise that corresponds to bit 1. Let us call this as n1. Now you must remember that the variance of this noise source will be different. The variance of sigma 1 square is different and in fact larger compared to sigma 0 square. Why? Because sigma 0 square is only thermal noise, whereas sigma 1 square will involve thermal noise as well as short noise, right, and short noise is actually dependent on how much input power you have or how much optical power you have transmitted. So, this would be the condition, but when will I make this error? When will the receiver think that you have transmitted a 0? When the photocurrent value actually falls below the threshold current value, right. So, when the photocurrent value falls below the threshold current value, then we declare this as a bit 0, okay. Although in practice actually what has happened is your received input was supposed to be higher than the threshold if there was no noise, but the noise has gone so negative that it actually dips the value there, right. So, it actually dips the value, and that is the probability that we are trying to find out. So, when this IK1 becomes less than ITH, and what would be SK? Oh well, SK should be R P1R, right. So, this is the photocurrent that you have obtained is R into P1R, where P1R is the optical power that you have received. R stands for the responsivity. In the absence of noise, this is what you would have received, but in the presence of noise you are going to get N1 as well, okay. So, let us write down that one. So, you have R P1R plus N1 being less than the threshold current, right. When will this happen in terms of the noise variable? When N1 is less than ITH minus R P1R, okay. When this happens, you are going to get an error, right. You can turn around this equation by multiplying by -1 on both sides, and when you do that you are going to have to also change the integral limits over here. So, this fellow is equivalent of N1 being greater than RP1R minus I threshold, okay. So, when this noise process actually happens to be greater than this one, then you are actually going to be in the situation where you are looking at the error there, okay. You can work in both domains, you know, or both expressions, does not really matter. For simplicity, let me take this one as an example. Going in from this expression to this expression is fairly simple for you, so I will leave that as an exercise, okay. So, what is the probability that the noise N1 would be less than ITH minus R P1R? What is the probability that this noise would be less than this? Well, this would be the situation when I have to integrate. So, if I look at the probability density function, the probability density function for bit 1 will have a variance of sigma 1 square, okay, and it would be the area that you are looking for is when the noise actually is less than this particular value. So, this value, let us call this as ITH minus RP1R, and you are looking for the area under this one. But area under this is actually equivalent of finding the area here, right, and then subtracting from 1. So, the area in the blue lines is actually 1 minus the area of this. If you want to find the probability of this event itself, that is when the noise is less than this one, well, you can do that, but this time you have to integrate from this fellow all the way up to minus infinity, right, or you have to integrate from minus infinity all the way to this ITH minus RP1R. So, integrate this one minus infinity to ITH minus RP1R, the function will be 1 by 2 pi sigma 1 square, it is not sigma 0 square, and then you have e to the power minus n1 square divided by 2 sigma 1 square dn1, okay. You can do a change of variables over here. I will just introduce you to that one and I will leave this as an exercise to you. So, change of variables from n1 to n1 by sigma 1, define it as t, and then change the limits appropriately, change the integration variable appropriately. You do all this simplification and you will see that this is simply 1 minus q of r p1r minus ITH divided by sigma 1. So, in terms of the q function, this is what you are going to get, okay. This is of course makes sense, right, because this one is RP1R minus ITH divided by sigma 1, okay, and from that area 1 minus of that is what you are going to get as the area under the other portion. So, you have to do this one little carefully to see that this expression is all right, okay. Once you have done that, now you can put together the total error. How do you put together the total error? Suppose you have bit zeros and 1, right, in the on off keying, that is what we have. When you transmit 0, there is a certain probability that the receiver will identify that 0 as 0, okay, that is given by probability of 0 given 0. However, this is what you are interested in, the probability that, so this is 0 and 1, the probability that the receiver has identified it as a 1 although you transmitted a 0. Okay. Similarly, this link or this line will tell you the probability that the receiver thinks you have transmitted a 0, but you have transmitted a 1. So, these are the error components, and this is the probability of the correct decision, that is probability that you have sent a 1 and the receiver also thinks that you have sent a 1, okay, decides in favor of 1. The probability of error is, of course, what is the probability that you have sent a 0 but you end up being 1, and that would be probability of 0 times probability of 1 given 0. Okay. So, this is where you end up making an error, plus probability of 1 and probability of 0 given 1. Okay. Of course, we have also assumed that these two are equiprobable. If they are not, then you have to weight the threshold current appropriately, but if you assume that these two are equal, so each of them will be equal to half, and the probability of error will be equal to half of Q of ITH by sigma 0, okay, plus 1 minus Q of R P1R minus ITH divided by sigma 1. Okay. So, this is what the probability of error is. Okay. So, with this as the probability of error, our next question is what value, okay, of ITH will minimize PE. What value of ITH should we choose such that the probability of error will be minimized? Well, the straightforward answer to this one is that you have to differentiate this PE with respect to ITH, set this to 0 and then find out the value of the threshold current which would minimize the probability of error. Okay. Doing this is unfortunately not so simple. You have to do some rules that you have to know for the differentiation that you normally are not aware. So, I will leave this as an exercise or as an assignment for you, okay, and I will tell you how to solve this one in the assignment, right. So, if you excuse this step, then kind of a hand waving argument can be made, okay. We have these Q functions, right. So, when you differentiate this one, they are going to go to 0, right, but if you look at the probabilities of these errors, this would be the probability of making an error when you have transmitted a 0 but you think it is a 1, and this portion will be the probability that you make an error when you transmit a 0 and a 1, right. If you take the arguments of each of these Q functions and equate them, then you have kind of distributed the errors equally. So, both the errors are equiprobable, and that happens when the threshold current by sigma 0 is actually equal to RP1R minus ITH divided by sigma 1. Okay. This is what when happens. When you are short noise limited, okay, you do not have thermal noise, but when you have short noise limited, when do you get short noise limited? Well, when you get amplifier in the loop, right. So, you get a pre-amplifier in your circuit, or you are looking at the coherent receiver. Okay. When you have a coherent receiver, these are short noise limited, for which case sigma 0 will be equal to sigma 1, and what will happen to ITH? ITH is equal to RP1R minus ITH, or the threshold value that minimizes the probability of error is given by RP1R by 2. So, this is the halfway mark between what you receive as bit 1 and what you receive as bit 0, but this threshold works only when you have a short noise limited, okay. And since RP1R is nothing but the current I1 that you have received, okay, you can then go back to this expression in the case when sigma 0 is not equal to sigma 1 and find out what would be the value of I threshold. Okay. I threshold is given by, or rather I threshold divided by sigma 0 is equal to I1 minus I threshold, and there is a sigma 1 here. I pulled out the sigma 1 that was there in the denominator onto the numerator. You can simplify this equation, you get 1 plus sigma 1 by sigma 0 over here when you pull this ITH back onto this one times ITH equals I1, okay. Simplifying this relationship, I threshold, which would be the optimum value, will be given by sigma 0 I1 by sigma 0 plus sigma 1. You further can consider the case when I0 is not 0, I0 being the current that you would receive when you have transmitted a bit 0, that is when the laser is supposed to produce 0 power, but in fact it produces a non-zero power because of the problems with the laser itself, then the current that you receive, the signal photocurrent that you receive when the bit is 0 is not exactly 0, and that can be also incorporated. If you go back to this expression, and instead of writing this as ITH, you can show that it should be ITH minus I0 divided by sigma 0, which should be equal to I1 minus ITH divided by sigma 1. Solving this equation will give you the threshold current as sigma 0 I1 plus sigma 1 I0 divided by sigma 0 plus sigma 1. I will leave this as an extremely simple exercise for you to work out. Okay. So, what we have looked at is, this is a kind of a hand waving argument. We have not really derived that these are the optimum values. In fact, the expression for the optimum value is quite complicated, and in the assignment you will see how to differentiate the expression for the probability of error in order to find out what would be the optimum value of the threshold. But what is interesting in all this, and whether it is hand waving or something, is that unlike a radio receiver where sigma 0 is always by default equal to sigma 1, for on-off keying optical communications it is not. The short noise that you get is dependent on the input optical power or the received optical power, and different receivers actually respond in different ways, right. Suppose you consider the simplest case of a pin and an APD receiver. Okay, you do not have an optical preamplifier in the loop, you simply consider a pin or an APD receiver. First consider a pin receiver. In the pin receiver, sigma 0 will be purely based on the thermal noise, and sigma 1 will have both thermal as well as the short noise. Okay. And for a given value of this Q factor which we had defined, and now here is a small problem, this is the Q factor which we had defined as I1 minus I0 by sigma 1 plus sigma 0. This is not to be confused. So, not to be confused with Q function. It is unfortunate that we have used the same expressions for both, but that is how life goes. Okay. So, you have the same notation, but the context should actually tell you the difference. So, if you look at this Q value, okay, or if you want you can call this as some gamma value, does not really matter. Okay. So, this value is the one that determines what would go into the probability of error, correct. So, this is what determines what would go into the probability of error, and this factor will be different for different receivers. For the pin receiver, okay, so suppose you want to obtain, let us say, a BER of 10 to the power minus 9, okay. This means that in the expression for the probability of error, after you have chosen the optimum value of the threshold correctly, then you need to have a certain value of gamma such that Q of gamma is the bit error rate, right, or this is the probability of error. And for whatever gamma that you choose, right, so this gamma should be around 6 dB for the case where you are considering 10 to the power minus 9 bit error. Okay. And this gamma is the one that goes into this particular expression. Okay. So, if you have received a certain power, then Q factor that you set is the expression that goes into the Q function. This ratio of the current to the sigmas is the one that actually determines the Q factor that goes into the Q function, which then determines what would be the probability of error. Now, what happens is that for the case of pin diode, sigma 0 is sigma thermal, sigma 1 includes sigma thermal as well as sigma short noise, and if you look at resulting values that you want, assume also that I0 is equal to 0 just for purposes, then the gamma factor, which is I1 divided by sigma 0 plus sigma 1, and I1 is nothing but R P1R, okay, and you can go back and assume that R is equal to 1, this is kind of an ideal scenario, then the required received power should be gamma times sigma 0 plus sigma 1, okay. This is what you require. On the other hand, if you are looking at an APD receiver, because the current I1 will be multiplied by the multiplication factor of the APD, so it would be R GM P1R, you would see that the required P1R is given by gamma sigma 0 plus sigma 1 divided by GM. Already without doing any calculation, you can see that this is APD which requires this amount of the received power, whereas P1R requirement has gone down by a factor of GM. What it means is that if you look at a function of the bit rate, right, the sensitivity of a pin diode is the worst, okay, whereas because there is a large gain factor GM, the sensitivity of the APDs is much better. So, this fellow is the APD, and you see that the received power requirement for the same BER is actually much lower for a given bit rate in the case of an APD receiver, okay. And this is the internal gain, this is because of the internal gain of the APD structure itself, okay. However, with APD what would be the noise sources? Well, there is thermal noise, okay, which you will anyway get when you have sigma 0, but when you have sigma 1, that is when you transmit bit 1, you get thermal noise as well as this short noise, but this short noise gets multiplied by a certain factor, right. So, there is the GM square FA of GM, where FA is the noise factor or the excess noise factor of the photocurrent, right. Because of this multiplication which happens, the short noise component actually increases with sigma 1, okay. The short noise that you get with an APD is much larger compared to the short noise that you get with a pin diode receiver. However, you can show later that the required optical power actually goes down when you have this APD receiver, okay. Moving on to next case where you have optical preamplifier, okay. In the optical preamplifier case, what would be the major noise factor? Well, is the signal beating with the spontaneous emission being the major noise factor, right. So, because of this would be the case when you have transmitted bit 1. For bit 0, you have spontaneous, you have thermal noise, you have spontaneous noise, as well as you have some amount of short noise. Short noise is actually equal to 0 because you have transmitted bit 0 here, okay. What you get is only thermal noise and spontaneous emission noise, but these values are so small compared to the signal spontaneous noise beating that one can kind of neglect this in the expressions for the received power or the sensitivity of the receivers, with the result that the sensitivity actually goes better with respect to optical preamplifier. So, for the same bit error rate and for the same BER, the power requirement for the preamplifier goes even further down, okay, and that is all happening because of the signal and the spontaneous emission noise process. We have already looked at this one, go back to the previous modules to exactly see the expression for the signal spontaneous noise source. Finally, when you have coherent receivers, we have also looked at what happens with the coherent receivers. The short noise component for when you transmitted bit 0 is the same as the short noise component when you have transmitted bit 1, and this happens because both are LO limited, right. It is the local oscillator power which determines the short noises, and this overwhelms all the other noise sources in the circuit, okay. And because of this you actually gain even more. So, you actually gain a 3 dB sensitivity improvement with coherent receivers, okay. So, the last one is the coherent receiver. If you fix your bit rate, you see that the worst is a pin receiver which requires rather high power the receiver to detect. The next is the APD receiver which already gives you better sensitivity, but that is not completely sufficient or that is not completely good compared to a preamplifier which increases sensitivity even better. Finally, you have a coherent receiver which actually performs even more wonderfully than a preamplifier. This line also indicates the increasing complexity, okay. You have a pin receiver followed by a transimpedance amplifier, that is the simplest kind of a receiver that you can think of. APDs, they are little more expensive, have to do have to make with increased complexity in the circuit because the power requirements for a reverse biased APD is slightly higher, much higher than the pin receivers. So, it is slightly more complex. Preamplifiers require you to actually install an optical amplifier which is even more complex, and coherent receivers is the complex of all because it requires polarization tracking, phase tracking, as well as the frequency offset being constant or equal to 0. So, complexity increases, but what pays off is the increased sensitivity. So, the larger the resources you put in, the larger in this particular case would be the sensitivity of the receivers. So, this is what we wanted to talk about the on off keying receivers, and we will end our module today with this one. We will later look at other modulation sources and some residual effects in the fiber that we have not considered in the next modules. Thank you very much.